Great, thank you. So I'm Joey Eremondi, and this is joint work that I did in Edinburgh with Ohad Kumar. And we're going to be talking about coverage semantics for dependent pattern matching. So first off, I'm just going to give the real broad overview of what we're talking about and what kind of state the project is in. So this is definitely a work in progress, and I'm presenting it here because I'm leaving Scotland at the end of the month to start a faculty job in Canada. So I'm trying to get feedback and ideas and find out if someone did this all in the 80s, as sometimes happens. And so what are we doing? We're trying to give denotational semantics to pattern matching. Specifically, we're looking at top-level patterns. So like you would see in EGDA or IDRIS, where pattern matching is kind of tied to these top-level function definitions. And I'm specifically looking at non-overlapping patterns, and I'll talk a little more about that later. But the experiment that we're doing is, can we abstract over what we consider a pattern and which matches we consider as a set of total matches, as totally covering a type. And to do this, we're going to get into some kind of very basic sheaf theory and use the languages of coverages and Grothendieck topologies. I know it's basic because I didn't know any of it 6 months ago. So we're just kind of scratching the surface. And so what I'm going to present here is somewhere between a new viewpoint and a new result. It's we're kind of taking things that already existed there and putting them together to give a new way of looking at, and it gives us something similar to the way we already do things, but from a new kind of viewpoint. And yeah, if this has all been done before, let me know, because there's a lot of smart people here. So first, let's talk about dependent pattern matching, what it is and why it's interesting and what the kind of challenges are. So in dependent types, say we've got a function like this, repeat. So you take a number and then some element, and you get a vector containing exactly n copies of that element. And to do this, repeating something 0 times is nil, and repeating something n+1 times is that attached to repeating it n times. And so what's interesting here is, because these are dependent types, the return type, which is a length index vector, depends on what concrete value you give for n. And when you pattern match, the type of that n, or the value of that n in the type, gets refined. So in the nil case, we had 0 as the pattern. And so in the goal, in the type of the thing on the right-hand side that we're trying to produce, that gets changed to 0. The pattern rewrites what the goal type is. And it's the same thing in the successor case, that the type of the thing we're trying to produce when we match in the successor case replaces n with successor in the right-hand side. And the usual way of defining semantics for pattern matching is to go through eliminators. So for natural numbers, you've got some kind of type parameterized by a number, and this is usually called the motive. It's the target type. And it says, you give me an instance of the motive for 0, and you give me a way to build an instance of the motive for n+1, given one from n. And then I can build an instance of the motive for any n. So this is basically exactly what the induction principle is. And so in terms of semantics, this corresponds to basically initial algebras over polynomial functors. And the more complex features of pattern matching that we see, at least in terms of kind of the semantics on paper, these get defined by elaboration into these primitive eliminators. And so we've known how to do this for quite a while, and there's various flavors of this that happen with axiom K or without axiom K, and but this is the kind of usual way to do it. But one of the things we're going to look at is, can we do this? Can we skip that pass through eliminators? Can we give semantics directly without kind of this intermediate step? And so to kind of give a little bit of motivation, or at least kind of the sort of thing we're talking about, I'm going to give a crazier way of writing that same function. So we're creating n copies of something in a vector. But we could instead say, well, if you've got 0 of something, is the empty list. If you've got an even number of something that isn't 0, well, then you just take take the half of it, make it twice, cons it together, and add 2 more to the start. And if you have an odd number of something, then you can add 1 and recur that way. And so every natural number is either 0, non-zero, even, or odd. So this is a, this is a total way of covering the natural numbers. And if you were to use something like difference lists instead of vectors, this would get you a faster algorithm because it'd be log time instead of linear time. But really kind of the question we're looking at is, does something like this make sense? Now, I'm sure there are people who are saying, yes, this is views, and it totally is something you can do with views. But to do views, you would need to define your own data type, and then you need to write helper functions for that data type and work with it that way. And so kind of the question we're asking is, so to a lesser degree, can we do things like I showed you in that last slide? But also, can we come up with a broader set of criteria that says, okay, we have some crazy kind of pattern matching we want to do. What are the criteria that we need to fulfill in order to know that that makes sense, in order to know that pattern matching in this way is something we can give semantics to, something we can get a logical language out the other end. And so that's what this line of work does, is we identify some of those criteria. So the general idea is we have an abstract notion of coverage. So we're saying in our semantics, we've got we're leaving it abstract exactly which sets of patterns can form the left-hand side of a pattern match. We're not saying it has to be constructors. We're not specifying yet what it means to be total. And we're not specifically not defining the semantics in terms of eliminators. And the research question that we're asking is which coverages, so which ways of defining what a valid set of patterns is, will lead to a language that makes sense, that has denotational semantics, that's logically consistent. And the way that we're doing this is we're drawing from some category theory, and there's something in category theory which is also called coverages, which is basically here, I'm going to end up talking about it a little more, but the basic idea is we're looking at these kind of categorical coverages, and we're going to say that things make sense when you can define your covering set of patterns in your source language in terms of a covering family for this topology that you've defined in terms of your target language. And we're going to use some of the kind of elementary results from sheep theory. They're going to give us the kind of combinators to build up these coverages and the metric to determine which of these are good and which of these make sense. And so the kind of intuition of this is that, so a sheaf, I'll talk a little bit more, but the sheaf gives you a way to amalgamate things over a coverage, and we're going to use that amalgamation to define the semantics of matching. So what's a sheaf? And how does it relate to what we're talking about? So if we've got some object and then a bunch of arrows into that object, so that could be in our setting, the objects are types, and the arrows are the terms containing variables from their sources that are the patterns we're talking about. So those U1, U2, UN, those could be like the pattern variables, and then U is the target type. And then if we've got some pre-sheaf over that, so that's a set for each of those objects, and then a backwards arrow mapping between those sets. So a sheaf is a pre-sheaf that says, if you give me one element from each of the things in those UI sets, then there's a way that I can glue those all together. There's a unique way to glue those all together such that it's always going to factor through the projection. This is a slightly simplified version. There's a more complicated criteria when there's overlapping, but we're assuming things are non-overlapping. So basically it's saying if you give me one of the things from the set of each of these sheaves, or each of the sets from the pre-sheaf, and I can glue them together in a way that always factors through those initial arrows that you gave me. So what does this look like? Like, we left that kind of sheaf completely abstract. What does this look like when we look at representable pre-sheafs, which are these sets of arrows in our category, or sets of kind of terms parameterized over variables of a certain type? So in that case, what we get, if our pre-sheaf is the Yoneda embedding, what we get is so we've got terms of T with U variables, and then same for all the UIs. And it says, if you give me a T term that contains U1 variables and a T term with U2 variables, one of each of those, then I can glue those together into a term that contains the variables from U, such that if the initial thing that you give to this, such that if it came from this F1, if that's how it was built, then you will get this U1. And if it came from F2, you will get this U2. And this should be sounding somewhat familiar, because this is basically exactly what non-dependent pattern matching does. It says, if you've got some motive type T, so that's the target type, the thing we're matching into is the thing we're taking Yoneda of. And you've got branches, which is, so the first branch is parameterized over the pattern variables of the first thing, the second branch is parameterized, and so on and so on. Then the match construct says, well, I have a thing that is parameterized over whatever the scrutiny type is, and I can take that and I can give you a T regardless of which of the constructors or patterns, or however you want to say it, regardless of which of those was used to build it, such that this holds, which is basically just saying, if you gave me something built with the constructor for I, or the pattern for I, well, then that is going to go to the branch I. That's what it's going to give as the result. And so this the coverages that have this property are kind of known in sheaf theory because they're called so the coverage is just the general way of referring to the collection of all of the sets of patterns that we call valid, or all of the sets of arrows that we call covering. And the term for something where all of the representables are covering, that's a subcanonical coverage. And so again, this is something that existed for a long time. And then if you look at all the subcanonical ones, it turns out there's a biggest one called the canonical coverage. And the central kind of claim of the work that we're doing is that as long as you've got a category, you can model pattern matching over that category for any kind of legal left-hand side patterns, as long as each of those corresponds to some cover in the canonical coverage. And so what we get from this, as I'm going to show in little slides, is now we can draw from all of these existing results and these existing theorems from sheaf theory about how to create these canonical coverages, or what is in the canonical coverages, and how to put them together. And this isn't necessarily bidirectional. We're not necessarily saying we want our source language to have everything that's in the canonical coverage, because that's probably going to be very, very undecidable. But it at least gives us a criteria that we can say, we want to add this new feature. Is it sane? Does it make sense? And this is something we can use to judge that. Now, some of you might have noticed, I said that this corresponded to simple pattern matching. How do we get dependent matching from this? And so this is one of the cases where the sheaf theory starts to pay off, which is that if we have our category, we can do a slice of that category. And that's basically a way of saying the objects of the initial category indexed by something of type T. And it turns out that if you've got a subcanonical coverage on your category, then every slice you also get a subcanonical coverage on that one. And in particular, you get this as a covering family. Basically what that lets you do is it lets you do the gluing of the branches together for a dependent pattern match, and the kind of side condition on arrows of the slice category is exactly what gives you that you get the right index from your dependent match, that the result of applying something, that index corresponds to whatever the actual value of the scrutiny of your pattern match was. And so now that we've got our criteria, can we actually build up pattern matching that looks like something even, do we at least cover what we have already for pattern matching? We're going to use, from sheaf theory, there's some things called saturation conditions, which is basically a way of saying, if you've got all your sets of covering families, these are ways you can change it that won't change what is or isn't a sheaf. And so, of course, that means that everything for these saturation conditions must already be in the canonical coverage, because otherwise it wouldn't be the biggest, because you could do this operation and add more things into it. And so the kind of key ones we're using is you can have any isomorphism as a covering family. So the singleton containing just that isomorphism. You have composing coverages. So this basically says if you've got some covering family and then some set of coverings for each of the things on the left of that initial thing, you can compose those together. And then the kind of interesting one that I will have to talk about very quickly is you can pull back by any arrow, and the coverage you get after that is the same as the initial thing. So basically, each of these correspond to a feature from pattern matching that we want. So the base case is we want to be able to match to a variable. You need to be able to say, I'm matching on this thing, but this is a wild card. I don't care what pattern it has. And that works because the identity is an isomorphism. We want to be able to match on equality. And that works as long as in your kind of model category, you've got a type A is equivalent to X and Y from A such that X is equal to Y. As long as that's an isomorphism, then you can match on REFL. And what's interesting about this is it doesn't at any point require that your equality is an inductively defined type. So if you've got observational type theory or some other kind of thing where equality is not an inductive type, you can still pattern match on REFL and you can still get something that makes sense semantically. So this isn't a saturation condition, but just a general kind of thing we want is that if you've got some coproduct in your category, the injections into that coproduct are covering. And this works as long as we've got, basically, if your category is locally Cartesian closed, which it probably is already if you're modeling dependent types. So this gives us that, first off, if you have the constructors of your data type, they will form a coverage. So that's good. That's what we already have from pattern matching. We want that. But there's, again, no actual requirement that those be constructors. If you can find some other way of decomposing your type into a way that the coproduct of those functions is the type itself, then you can pattern match on that decomposition and get a sensible way of doing things. And then that kind of composition rule I told you about before is basically saying if you've already got a pattern match, you can split on one of the variables in that match. So it's like in AGDA, you hit Control-C and you get more branches from that specific case. So that's what that gives us. So we're able to cover most of what we already have from pattern matching with these. And then it turns out that pullbacks are exactly what we need to pattern match on equality and get this unification that happens with dependent pattern matching. So as an example, we've got 3 numbers and we're matching on a proof that the first 2, if you add them together, you get the third one. And when you do this, you can match on it. And when you match on that REFL, is going to rewrite basically go back in the context and say, well, if this is REFL, I know that R must be P plus Q because that's the only thing. In EGDA, that would be a dot pattern, but we're basically doing dot patterns without the dots. And so we can get this from that pullback quality. So we've got the covering, we've got XX REFL is a cover of XY, X equals Y. And then we define this other function that says, okay, here are all of the things in context and the equality that we're matching on. And if we pull back, so for us, we've got PQR and an equality, and we turn that into the pair of things we're equating and the equality. If we pull back between these two, we get exactly that pattern from the branch there, the PQ, P plus Q, because that's exactly what you need to factor through. And the reason this works is because pullback is basically the semantic version of unification. It's giving the most general way of making these two things equal. And so the pullback saturation condition says that you can do this, and then the thing you get as a result is fine to be a singleton covering family, that's the only case you need to handle. So this, again, gives us a kind of semantic justification for pattern matching on equality, and then the way it goes back and rewrites those dot patterns for previous values, but it does it in a general way that doesn't require us to assume we're dealing with inductive types. Now, there's some limitations to this, like I talked about a bit. Just because we can define a semantics doesn't mean you can decide it. And this is all implying axiom K, because this pullback I talked about, that's assuming this kind of strict notion of equality. It implies the deletion rule, which is the thing you need to get rid of to have pattern matching without axiom K. So it's currently incompatible with homotopy type theory. I'm guessing you need like infinity sheaves or something higher to give more structure than a normal pullback to model those things. And the other kind of limitation is this is requiring a lot of extensionality in the model. So what's next? As you probably have noticed, I haven't dealt at all with recursion or termination, so that's something to work the details out on, and then extending this to more sophisticated pattern matching, so pattern matching in deeper terms, not just at the top level, and with patterns, although I think that's going to be related to pullbacks. And then finally, the thing that got me into this whole project is modeling overlap, saying, okay, when your patterns aren't all disjoint, how can we model the way they overlap and get better semantics than the status quo, where you have to do this kind of n-squared explosion when you're proving something about a function that's defined with a wildcard. And then I'm hoping there might be some deeper connections with topos theory, because like I said, we're really only scratching the surface of all the theory that's available there. So that's all I've got today. Thank you.
Okay, questions?
Thank you, that was really cool. I've got two questions. One is, can you do things like, so there's nice things with functional languages which aren't independent, things like OR patterns and guards. Can you do things like that?
I haven't thought specifically about it. You probably could.
OR patterns should be some extra structure.
Yeah, because you need to kind of make sure that they have the same context types, and or at least that you only refer to the things that are common between the two contexts. I'm guessing there's a way to model that in terms of like the like coproduct of two arrows, or like the bimap of them or something. But I don't hold me to that, because I haven't put thought into it. Yeah, that's a really cool idea, and I will have to think about it, because yeah, that would be really great if we could model that better.
Yeah, and the other thing was, it looks very related to the use of sheaves for NBE for sums. Is that something you thought about? Or-
It's probably related. Full disclosure, I kind of came into this with not a lot of sheaf or even category knowledge. So it's probably related in a way that is much deeper than I know. But I'll definitely have to take a look at that because it could be, it could be that there's a connection there. Thank you.
Thank you. Really nice talk.
Thanks.
This is somewhat related to your very last point, or like the one before your very last point, where you're saying maybe you could get more equational theory for overlapping patterns. Have you thought about, now that you can talk about stuff in an arbitrary category, could you drop down and say, okay, this definition assumes I'm symmetric monoidal, for instance, and so my definition will be commutative, will be commutative by construction. Like I could define min maybe in a way where then internally, automatically in judgmental equality,
Right.
I know that it is commutative.
Probably. So I haven't put a lot of exploration into the specific category. I've kind of by design been just trying to keep everything as general as possible. I think you could get that. I don't know if you could get it definitionally in the checker. So you could definitely get it where it holds in the model, where it would be safe to consider them definitionally equal. But I don't know how you would then turn that into something your type checker could do as an actual condition to check to say, are these two things equal, or is this actually commutative? But that's it's also possible that I'm not, kind of not fully understanding how that works. But yeah, I think that would be a really cool future way to take this. Thank you.